Hello, everyone. Good morning, good afternoon, good evening, depending where you are in the world. This is the LAMPS working group. Basically, our agenda was too full at the IETF 121 in Dublin. And so we scheduled this to deal with a few of the presentations that we did not get to. The normal housekeeping. The first one is we need someone to take notes. Can somebody please take notes in the online Etherpad tool? We can't get started until we have a note taker.
I was just going to say, I can take notes, Russ, if no one else wants to, or someone else. Except when I present, someone needs to take notes for when I...
Okay, who can back John while he's presenting? I need to run the meeting, so I can't do it.
I'll be in the notes, and I'll try to back John up.
Thank you very much, Michael. All right, thank you so much. So, reminder that this is the IETF and we operate under the note well. Please don't participate if you haven't checked out your responsibilities for contributing. And please treat everybody with respect. It's okay to attack somebody's ideas, but not to attack the person bringing those ideas. And as this is an online meeting, please make sure your audio and video are off unless you're chairing or presenting. Headsets tend to help reduce the background noise. And of course, this session is being recorded. This is the agenda. Moments before the meeting, I updated the agenda, but not the slide, to add if time permits briefing on recent updates to the composite documents. But the ones that are on this slide are the things we did not get to in Dublin. And if this does not take all the time, we will head off to hear an update on composite. There any questions on or agenda bashes at this time? Okay, so given that, we're going to start with the EUF CMA presentation. Okay, Falco,
Yep.
I'm going to try and pass you the control if I can remember how to do that. Pass slide control. Okay, you should be able to control the slides now, and I'll turn off my audio and video.
Yeah, I have the control. Okay, thank you. Okay, so we presented the first part already during the last meeting, but I think the idea is to present it again to have a consistent presentation of the whole problem. So the problem is summarized in this paper, but actually not all aspects of the problem. The paper still needs an update to account for both types of attacks that are presented the following. But it is at least showing one of the attacks in quite some detail. But actually, it's rather simple. What we are dealing with is in CMS, the signed attributes and their presence or their absence, and how this can cause signature forgeries. So the signed attributes are a structure which contains can contain various attributes, but one of them is the message digest attribute, which always has to be present, which contains the hash of the message. So, and we'll use this notation in the following, with the signed attributes, the DR encoded signed attributes for the message M to indicate that they contain the hash of the message M. Now we look at the ASN1 definition of the signer info, where we see that the signed attributes are an optionally part of them. This is the source of the problem, as we will see. We look at the algorithm for signing in CMS, and this has two variants. One, when the signed attributes are absent, then the digest is just computed as the hash of the message. If they are present, then the digest is computed as the hash of the signed attributes, which, as we have seen, in turn contain the hash of the message, but also further information. And then the signature is computed over this digest D. Now we look at the first type of attack, where the attacker can choose a message of a specific form for which he achieves a signature that the signer never created consciously. So the attacker just supplies the message M of the form of signed attributes for a message M prime, which he can choose, and then the signer assigns this message. But this can, of course, now not be distinguished from the case where the signer signed the signed attributes for this message, and then all the attacker has to do is to exchange the message and to add the signed attributes to the signer infrastructure. In this way, he can forge signatures for arbitrary messages M prime. The other way is, of course, when the signed attributes are present when the signer is signing, then there's automatically a message M prime for which the signature is valid as well if the signed attributes are removed from the signer infrastructure. In this case, the signatures, the messages for which we have a forgery, are of the form of the signed attributes. Now, there are clearly some protocols which are not affected. These are all the protocols which declare the presence of the signed attributes as mandatory. This is a SCEP, certificate transparency, and some other protocols. Also, when the message is signed and encrypted, the attacker has no way to get to the signature, so he's not going to be able to use it for forgery. But there are also some ideas when systems can be vulnerable. So first of all, there must allow for the absence of the signed attributes. We could have something, for instance, like an unencrypted firmware update, which is just then replaced by this structure that has the form of the signed attributes, which will not let the device boot, and maybe the device is bricked. There might be protocols with dense message space and machine-to-machine communication, for which the signed attribute structure is, for instance, a valid message. Then there might be a protocol that sign unstructured data. And yeah, this I think is enough to discuss at this point. And then we come to the second part, which will be presented by Daniel.
Hi, I guess you'll still have to manage the forward and backward of the. Oh, no.
Okay.
Oh, Russ handed it to me, so.
Great.
If I can figure it. Okay, so I'll present mitigation. We, excuse me. We wrote a draft since Dublin, which contains a number of options for mitigation. So I'm going to present those and then hopefully get feedback from the working group. How to move forwards next. Okay, so I'm doing this in reverse order from the draft. First, I'll talk about the application or protocol level mitigations from section 4, and then the signature context mitigations from section 3. So first we have attack detection during verification, where if the signed attribute structure is not present, the verifier checks if the signed message is a valid dir-encoded signed attributes and fails the verification if it is. This addresses variant 2, which Falco just presented, where the attacker removes the signed attributes. Given that the signed attributes must contain a certain set of attributes, this should mean that there's a low probability of a legitimate message being flagged and failing verification. But as Falco just mentioned, if there's a dense message space, then this might not be the case. For variant 1, where the attacker adds the signed attributes, this would need to be addressed on the signer side by the signer refusing to sign messages that look like a dir-encoded signed attributes. Carl Wallace had a number of suggestions on the list. Thank you for them. One of them was to apply the verification mitigation when the content type is ID data. It seems to me that this is the same as saying whenever a signed attributes isn't present, because any content type besides ID data must have signed attributes. That can be clarified on the list, I suppose. So next mitigation, the protocol could simply specify that it always or never uses signed attributes and enforce that check during verification. Or it could also move off of the ID data content type that solves the issue by requiring signed attributes. This isn't so much a CMS issue as a protocol issue. So I don't think there's much we can do about it in LAMPS except make recommendations for future protocols to not use the ID data content type or to update existing protocols. And maybe then we have to update SMIME to move off that content type as well, which maybe isn't trivial, I don't know. And then the third mitigation in this section is to do the same attack detection from the first mitigation, but in individual protocols. I guess I forgot to mention that the first mitigation was kind of intended to be across all of CMS verification and not a protocol specific thing. This is just doing that at a protocol specific specification. Moving back one section in the draft to section 3, we have mitigations which use the context parameter during sign and verify for certain signature algorithms. Apologies for the naming of these sections. They got pretty long. They made more sense when writing the draft, but putting them here, it's just kind of a wall of text. So I'll get on to those next 3, but it's worth noting that these mitigations only apply to signature algorithms, which can take context strings. For CMS, that means MLDSA, composite MLDSA, SLHDSA, and for some of the options, potentially ED448. This wouldn't apply to RSA or ECDSA, as well as for ED 25519, because the context variant of that isn't specified for use in CMS. The first option here, which I called immediate forced use of specific signature context strings, is basically editing the current CMS PQ signature drafts to use different signature context strings based on whether signed attributes is present or not. Then the signature won't verify if the attacker has added or removed the signed attribute structure. The advantages of this are that since it's written into the current CMS drafts, the countermeasure will always be in place. And depending on how you look at it, it could be good for this to be a forcing function for libraries to start supporting signature contexts right away. Disadvantages of this option are that it delays the current drafts, although since they haven't been through working group last call, it's something where we could add text pretty easily tomorrow. It doesn't help with ED 448 because RSC 8419 is already a thing. And then do we have to consider libraries that don't support signature contexts, or do we have to consider existing implementations of the CMS post-quantum signature drafts? The second option in this section is basically defines a new unsigned attribute, which specifies whether signing and verification should occur using a signature context string. If this attribute is present, then the appropriate string is used based on whether or not signed attributes are present. So the string would be potentially signed attributes or no signed attributes. If the new attribute is not present, then the default empty string is used for the signature context, just like what's written in the PQ/CMS drafts already. A verifier would need to check for the existence of this attribute and the existence of the signed attribute structure to determine which context string to use. An assigner would only include this unsigned attribute if it knows that the verifier understands it. Otherwise, the verifier wouldn't be able to set a different context string. And this would be done through protocol negotiation or SMIME attributes, maybe. The advantages of this option are that there's no changes to the in-progress drafts. It could be applied to ED 448 by updating RFC 8419 and possibly 8410. And it does give crypto libraries time to support the context string. Disadvantages of this are that it's an optional feature, so this could result in slow adoption. And we might need to say something explicit about ED 448, which could mean that libraries needing to expose the context string functionality for ED 448 would need to make changes if they haven't already. Although if they're implementing RFC 8032 properly, they should already do this. And then the final option is a different unsigned attribute, which contains a list of keywords and values, one of which is whether the signed attributes is used or not. The signature context is then this list or a value derived from it. And to mitigate the attack, the verifier would need to parse the list and check that the signed attributes status in the list corresponds to the existence of signed attributes structure. Maybe an advantage of this is that it's generic, or maybe disadvantage of this is that it's generic, too generic. Either way, Falco and I discussed this recently, and we don't really like this option because the genericness can lead to solving problems at the wrong level. Effectively, as long as the EUF-CMA signed attributes issue is fixed, then any other commitment that we want the signature to, anything that we want the signature to commit to should be done using a signed attribute and not part of the signature context. Finally, this is just a direct comparison of three of the options: the attack detection, use of the signature context in the CMS post-quantum drafts directly, and then defining a new unsigned attribute, specifically the one from section 3.2 that I presented 2 sections back. All of these cells are from previous slides, so I'm not really going to go over them. It's just here for reference during discussion if it's needed. And then with that, the question is, what would the working group like to do about this issue? Should it be addressed? If so, which mitigation method is preferred? Russ is in the queue.
So wouldn't it be more straightforward to write a BCP that says going forward always include signed attributes?
Yeah. So I think that was. Okay. That doesn't help existing protocols.
No, it doesn't. But a bunch of these have a transition time as well,
yeah.
Right? And so it seems to be getting to the better goal state. I mean, we're pushing in the right direction that way.
Yeah. So this proposal 4.2 is basically always or never use signed attributes.
Always and never. Okay. Well,
always. No, always or never. So we can just make it always.
Right. Okay.
And then that would be the BCP.
Yeah. Okay. Thank you. I would advocate that approach. We'll see what others think.
Deb.
Can you go back to the slide that says which algorithms need this, that have this problem? There's one, you had one with, you had MLDSA, most of the new.
So all going back or forwards? I'm almost at the
forward,
beginning.
I don't know. One way or the other.
So all algorithms have this problem. It's just that if you want to use the context-based mitigation, then you can only use an algorithm which takes a signature context, which is MLDSA, composite MLDSA, SLHDSA, and maybe ED 448 if we change some other RFCs.
So for that, the only thing that's already deployed is the ED 448, right?
Yeah.
To build on that, Deb, the 448 in CMS does not use a context string.
Right.
We'd have to update that RFC to do so.
Right.
Okay.
I'm just trying to see what's left over if you do what Russ says and write a BCP, saying from now on, do it this way.
Oh, well, this one, if we always do that, we don't need the context string. It's a design choice between those two.
Okay. Is this new to the working group, or has this been hanging around for a little while and I've just been oblivious?
Dublin was the first time we talked about it.
And you probably did it during the session I wasn't at.
We did it at the end of the last session.
Yeah, so I wasn't there. Okay. All right. So I'm just trying to figure out how oblivious I've been. So, thanks.
Okay.
Okay, are there any other comments? Go ahead, Deb. You're muted, Deb.
My session was hung. I don't know.
Okay, Michael.
So for CMS objects on disk, like emails, maybe, from 12 years ago, I'm trying to understand, there's probably not a risk of verifying the wrong thing, but I got the impression under mitigation that there was this thing where we could try to interpret something as a ASN1 and then fail. If it fails, then maybe we're being attacked. Did I understand that right, or did I not get it?
Yeah, so that would be 4.1, 4.3, basically. If we don't have assigned attributes in the CMS structure, but the message does look like encoded signed attributes, then potentially this is an attack.
So, but if it's a 12-year-old thing, the likelihood that someone did it is probably old because they probably didn't know to do it.
Yeah, could be.
But they can't insert this attack in an existing object because it's already under a signature, right?
No, they could
do this to an existing, manipulate an existing signature to do something.
They could, if they could get to your message store, right, they might be able to manipulate what you think is a stored message and apply this attack now.
Right. So the reason I'm keeping my signed email on disk signed is because I'm pessimistic about, stuff in the future or being able to provide evidence or whatever. So that's a real issue, I think, for someone who wants to use it as an evidence or something.
Yeah, I mean, so from Falco's presentation here, it has to be an attacker chosen message for both variants. So maybe it's not as bad an issue as that, because otherwise the attacker has to have some collision on a hash function or something. Whereas if they can get a signer to sign an attacker chosen message, then they can do whatever they want.
So, Michael, it's a bigger deal if you have stuff signed with MD5 or some weak hash function.
Although variant 2 says any message with signed attributes.
Yeah, it's just harder to find something that's not gibberish that would would match the.
Well, I'm thinking also about things like this would apply to like signed firmware, 8366 vouchers and other stuff that aren't necessarily emails, but
They still have to parse.
they still have to parse. So that's the point, is that you have to do a collision while still getting it to parse everything else out right. I'm just trying to understand that the historical on disk is probably not as threatened, I think, as going forward. People know about this.
I think so.
Go ahead, Mike.
Can't hear you, Mike. To the chat.
No, CMS does not allow empty signed attributes. In fact, when he showed the AS1, it shows 1 ... max. The actual answer is it's 2 ... max, because you must have a content type and you must have a message digest. You can then have others. Did that answer your question, Mike?
His question seems to be, what is the CVSS score of this attack?
Well, his first one was, are you allowed empty signed attributes? And the answer is no.
Right. His second question is, how critical is that we fix this? Are there actual practical attacks?
Right. That we don't know yet, I don't think.
Agreed. Lost Russ.
Okay. The queue's empty. Are there any other questions? Okay, thank you, Falco and Daniel. We're going to go on to the next presentation then. That is Draft Wang Lamps Root CA Cert Rekeying. Is Jillian here? Are you ready to present? There you go.
Oh, yes. Can you hear me now?
I do now, and I'm gonna.
Oh, okay. Thank you. Thank you.
I'm gonna
Yeah,
pass you
sorry for
control.
that. Yeah, my laptop does not work for my mic, so I have to use my mobile phone. So hope
Okay.
it is okay.
Can you
Yeah,
do the controls?
Probably. Yeah.
Okay.
Okay.
Go ahead.
Yeah. Next slide. Yeah. Already. Yeah. So actually, yeah, the main motivation for this draft is about we would like to propose a new root C certificate updated solution. Yeah, such that if someone for some legacy devices, they may not have the ability to update the trust anchor. device can still communicate with the updated new device. Yeah, they may belong to the same security domain, especially some device or equipment. Yeah, actually manufactured by the same company. Yeah, in such a scenario. So maybe our draft not writing very clear about this one. So a number of guests, yeah, gave comments about this. About the
I've lost his audio. Have others?
Yes, it's gone.
Julian, we're not hearing you. The data tracker seems to think, or the Medico seems to think he's, oh, now he's gone completely. Okay, Julian, what I think we're going to have to do is let you try and reconnect, and we'll go on to the next presentation and come back to you. Okay, Joe, I'm going to pass this to you. You have control.
All right, thank you very much. All right, good morning, good afternoon, good evening. I'm Joe Harvey here with John Gray to talk about a way we could do efficient OCSP PQC revocation using MTL mode. MTL mode behaves like a mode of operation for digital signatures. So I'll talk about the foundation of MTL mode, and then I will hand it over to John to talk about OCSP and how this could work within OCSP. All right, so first of all, what is MTL mode? MTL mode is a method for reducing a signature scheme's operational impact on expanding message series. So what does that mean? Well, rather than signing individual messages, MTL mode signs Merkle tree ladders. The messages are authenticated with a proof, a Merkle proof that goes to the rungs in the ladder. The ladders give backward compatibility. Instead of being a single root in a tree, they have a series of roots that can verify the Merkle proofs. So you can be backward compatible with things that have been signed, or future things can then be added to the series. This is very useful for series where you sign multiple things over time, especially like DNSSEC or OCSP, where you might have a whole bunch of stuff that expires at one point in time and needs to be re-signed. So there's two specifications. There's one that is for how you would implement MTL mode, and there's another that's considerations that explain how that could be integrated in application. Both these drafts are active right now. And there's also an open source implementation of MTL mode in GitHub that's available. So VeriSign does have some IP around MTL mode. We've done our IPR declarations. You can go there to see the language about that and about licensing for that IP. And with that, let me hand it over to John to talk about then how this works with OCSP. John?
Yeah, if you could keep controlling it, Joe, just because I have the hedge doc up on my screen as well. And yeah, it's
Got
kind of very small for me to read, so I'm going to read from my bigger screen. But yeah, so like Joe was saying, so if you go to the next slide, yeah, motivation. So I think it was, I don't know, a year or so ago, I think after they had presented the Merkle tree ladder proposal for DNSSEC, we got discussing a bit of things and started to think, well, what other ways could this be used? So what, the first thing that came up, at least when our discussions, was could this also perhaps be used in revocation? Because the way the structure works, anyway, if you go to the next slide, I'll get into more of the details. So think about revocation. So usually there's CRLs or there's OCSP. So with a CRL, right, so you have this big long list of stuff. OCSP changed that, right? So you have, I think most of you know this, so I'll just go over it very quickly, right? You have every single revocation status for a certificate is signed. So you have a lot of signatures. So if you had a PKI with 1 million certificates in it, you could have like 1 million basically signatures. So they all have to have a corresponding revocation status. They can change at any time, so that this is like the properties of like how OCSP works, right? They can change at any time. Obviously, something gets revoked, those things have to be replaced. And then basically the way OCSP works in most cases, not all, but it's basically their big caches of these responders that are pre-signed, right? So thinking about this in the terms of PQC, so now if you think OCSP, you know, they're very small, and now you're going to sign them with like MLDSA, which is, you know, a couple thousand bytes, and okay, that's going to kind of explode your system a bit maybe. So is there a better way to do this? So then thinking about it with MTL mode, if you go to the next slide, I think it is actually compelling. So as Joe was mentioning, so with MTL, right, so you have that structure, that tree-like structure, Merkle tree ladders structure going. So the root node of each one of those, like those are hashes, right? So instead of having a hash, each like OCSP response or revocation data that's signed, you could do a hash of the to be signed data. So that already saves you a bunch, right? So you're not having to do a signature on every one. You're just doing a hash of the to be signed data. So you can build this structure up. The neat thing with MTL mode as well, if you've followed it at all, is that there are two forms of the signature. There's a condensed signature, which is basically essentially the authentication path. So if you know how Merkle's trees work, there's this authentication path, like how Sphinx works and those types of things, right? There's an authentication path, but then so there's that piece of data, but then a full signature would be that authentication path plus a signature over, you can see in here where it says the rings and the ladder. So you have a signature. So you can imagine if you had, I don't know, tens of thousands of these, you could have one like PQ signature that can be used to essentially validate all authentication paths. So just thinking about it from that way, it's quite compelling. So if we go to the next slide, describe a little bit more about how that could work. Yeah, so, and depending, like MTL, there's, I'm not going to go into a lot of details, but there's different parameters that you can set it up to basically the size of the tree that you need, depending on how many certs you think you might have in your PKI system. And the neat thing with MTL as well is because obviously from time to time revocation status changes, so you can append new rungs to that ladder, so new things can be added. So if something gets old or stale, you just add new things, right? So that's quite compelling as well. So then, now thinking a little bit of the numbers, so we go to the next slide. So the pros of doing this, so we think that there could be a great performance benefit. So, I mean, if you think about it, you're going from what, N signatures. So if you had 1 million certs in your system, 1 million signatures to generate your OCSP or your revocation proofs, basically. And now you're basically changing that to hashes. So you're changing that from N signatures to N hashes. And then the signatures, it's going to depend on something called a batch window, right? So whenever you have OCSP, usually it's every day or whatever, 7 days or whatever your period is for your revocation data gets updated. I mean, obviously when that happens, you're going to have to do a new signature on that. Or if there's new stuff being added, there's going to be a new signature. But anyway, regenerating the entire tree is going to be a lot, very performant. The neat thing too is validation clients. So if you're a client and you're validating a lot of things, again, once you've downloaded that one full signature, then everything else after that, you only need the partial signature, right? So that's a huge savings. So in the worst case, if you're only validating very few things very periodically, then you're going to have a little bit of overhead because there's the Merkle tree ladder and some overhead on, I think, 472 bytes. But you have the upside, if you do more revocations more often, you're going to get a lot of performance benefit. So those things are really compelling. So then if you go to the next one, I think I'm getting close to the end. I'm trying to do this quick, and I hope it's not going over everyone's heads. So the cons, yeah, I think I already talked about that. Yeah, if you do infrequent verification, yeah, you're going to have to do that more often. And yeah, obviously there's going to be some more logic needed to maintain and manage the ladders and signatures separately from the authentication path. So you might be saying, well, why are we talking about this? So next steps, we were thinking about, well, we had started writing a draft on this, and we thought maybe before we actually spend all this time and effort doing that, we would just run the idea by the working group to see what you think. Do you think it's a worthwhile concept? And we have some ideas on how we could kind of prove out the performance numbers and things like that using a hackathon. So I guess there's some people in the queue. So let us know what you think. If this is, I think we would like to write an initial draft to describe how all this all works. But obviously, if people think this is not a good idea, then we can not waste our time either. So thanks. So Michael?
Can you go back to one of the things with the tree diagram, with the rung and the ladder? Yeah, thank you. So in chat, it's clarified for me that the newest items are the yellow ones on the right.
Yeah.
So I'm confused. I would have thought that the tree grows down and that the signature at the very top is the newest signature of the tree.
Hey,
well, yeah, go ahead, Joe. Yeah.
Oh, okay. So the way the tree grows is you add to those along the bottom, like there's 1 through 14. You keep adding the messages, and then each of those basically are binary trees that the root goes up and then merges into the tree. So the ladder is a collection of each of the roots needed to verify it. So in this case, the ladder would have 3 different roots that are tied together in the ladder. That way, if you want to check something and you've already got a path, say for node 7, you have a ladder and a path that verifies it, even if there's a 15 added, instead of needing to get a new root every time anything is changed in the tree. Does that make sense?
So in the ladder diagram, the rungs, I should read that from bottom to top in terms of the time sequence of the new signatures. There's 3 signatures. Do I misunderstand that?
Yes. So there's 3 rungs, and then that whole ladder would be signed once. So that way, if you added 20 things, you would re-sign the ladder once, and it would have however many roots are needed to verify those. So the backward compatibility stays of as long as 1.8 is a root, you can always verify those with that rung.
Okay, I get it now. Okay, so I see. So there's okay. So the second question is with OSPF stapling.
OCSP.
Yeah. So the advantage is that the client never has to do a second round trip because the server provides the staple with the cert. So in this case, he needs to have the signature on the ladder, and then the hashes. Let's say he's number 7. You said then he needs to have the hashes 1.8, 5.8, and 7.8 or something like that. It has to provide those hashes so they can be verified.
Yeah, that would be the authentication path. So that would be so as long as he already has that, that signature basically cached because he's retrieved it before, then yes, really anything under that's basically covered by that can be verified. So,
but in the pessimistic state, the server has no idea if the client has the signature cache, so he's going to have to provide the signature. If you just think of HTTPS, right? I go to a new website, I want the stapled OSPF from that with the thing, then it's going to have to be inbound, and I'm going to have everything.
Well, that's if you look at the considerations draft document, it talks about some of the different ways this can be done. You could fetch it out of band. It could be included as a retry mechanism, which is what DNSSEC is currently discussing, so that it stays in band. There's some different ways you could do that. It would depend on the draft for it and for OCSP in terms of what that would look like.
Okay, I'm not at this point buying that there's a savings of this more complexity for clients that care about reducing round trip times. That's all. Okay, next person.
Tomofumi.
Hello?
We hear you.
Thanks. Hi. I think it's a really good idea. New way to address the PQC issue around like revocation, and I look forward to supporting this idea at the hackathon.
Okay. Thanks.
So, based on the chat, there's a bunch of people who seem to have lost state. This Merkle tree ladder mode is being discussed in CFRG. What's new here is the applying it to revocation.
Yes.
And I just wanted to make that context clear because based on the chat, it was clear some people were not getting that.
Okay. Yeah. 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 This is applying it to the revocation domain. And I mean, I don't think at the end of the day, a draft we would write would be, it's not just going to be OCSP, right? There's going to be things like batch windows, and we've already had some thoughts about that. So it's not going to be just like OCSP plus. There'll be some other things that need to be in there, but we just wanted to like use OCSP as kind of the example of how using this structure could be an efficiency improvement. We believe so. Okay, Rich.
Yeah, since you mentioned at the beginning you have IPR declarations on this. Could you put them somewhere, a link to what they are, or maybe it's in the draft? Because given that it was discussed in CFRG in Vancouver, I'm just curious what. There's a basic
Yes.
OCSP. Oh, there they are. Okay, great. Thanks.
Yes. Yes, put them in the presentation because it's much easier to find it and read that than try to go through official language. Thank you.
Thanks.
Okay, great. Thanks. Alicia?
Hey, so one thing that's not clear to me is what are we optimizing for? Are we optimizing for the entity that is generating the OCSP responses, or are we optimizing for the verifiers or for the servers that ship them with the state link?
Yeah.
Who is benefiting from this?
Yeah, so the server side, so the generation of like, if you think about OCSP having to do 1 million signatures, now you're basically doing a hashes. So that's optimizing on that side, but also the verifier, so the client side. As long as you've already received that signed root node at least once, like you've already done one lookup, anything after that, you're saving a lot of, like, I guess maybe you should show the last slide it showed, Joe, that we had the extra slide that just shows the savings. So and again, this is in the context of PQ, right? Like larger signatures in the context of PQ. I think he's showing that one there. Yeah, you save quite a bit on the verifier side. Now, so it's always the subsequent one, right? The first one, you're not going to have big savings. You have a little bit of overhead, but everything after that, you have big savings on the verifier side. And then on the server side, like I mentioned, there's the generation of that entire tree is changing basically PQ signatures or into basically hashes. So that's where we think the performance benefit is going to happen.
Well, the thing is that we have been looking at the TLS certificates and compressing that stuff. And the result of the experiments was that basically it's not worth it. Because the client needs to tell the server what it has cached, and that basically doesn't scale from certificates. So I don't see how that would work for OCSPs, because it's basically the same thing.
I'm trying to think. I'm not sure I quite understand your question. I mean, OCSP.
Because we have basically a blob, which will be either the public key for the certificate or the signature for the OCSP response. And that's the thing that we are trying to reduce. So for the connections from the client can say, okay, I have this certificates, you can send just hashes of those certificates. Yeah, don't send me those, I already have them. And then the server says that, okay, you have those, so I'm not gonna send them, just use those ones that you have already cached. And from the TLS, it seemed that that's basically doesn't scale, doesn't work like that. And here we have basically the same thing. Like the client would say that, yeah, I have that large signature already, so just send me the part of the Merkle tree that I need for the verification. And but then like still you need to send that that root
you need
of
to send
the
the revocation data. Like the revocation data still needs to be there.
yeah.
Right. This is like, so you have revocation data and then it's signed. Instead it's signed, you can verify the signature using an authentication path, which is much smaller than, you know, the PQ signature or whatever signature you're using. That's where the savings comes. Okay, so I don't see anyone else in the queue. So I guess our next step was like, we didn't have a ton of comments, but we can take it to list. But if people think we should, I think we're going to plan to continue and write a draft unless you, I didn't hear a lot of people saying this is a really bad idea. Don't do it. I don't know if anyone else.
Yeah, but what I heard was some people skeptical about the actual gains, and sounds like the hackathon will prove or disprove.
Yeah, that's why we wanted to look at doing that. So, okay, so that's a good approach then. So we'll look at doing those performance, getting some metrics on that at the hackathon, and then potentially writing a draft based on that. Okay, thank you. We can give an update maybe at the next IETF then status on that.
Great.
Thanks.
Thanks.
Okay, we're going to move on to Tomofumi's presentation.
Yeah, I believe I'm going to present that one.
You're going to present. Okay, then do you want controls or not?
Sure. You can give me control. Let me just bring up that. And so, how do I do this? Ask to share screen.
It's already up. You just have pluses and minuses to advance the slides.
Oh, okay, okay, perfect. Yeah, okay. Oh, I see. Okay, perfect. Yeah, I'm gonna have to do it on my other screen so I can see it because I have the. Anyway, so yeah, so what this is, related certificate descriptor. It's a pretty simple update. It's basically used as a subject information access, an extension to that, basically so that you can help you locate related certificates. And as you can see here on the slide, it's the related certificate descriptor. It essentially has a uniform resource identifier, so a URL that you can use to fetch like a related certificate, and then two optional components, a signature algorithm and a public key algorithm, which you could use. The client looking at could say, well, do I support that algorithm in the first place? If I do, I could fetch this and maybe use it in a flexible way. So we believe it gives a more flexible way of cross-referencing related certificates. So I go here to the next slide. Yeah, so so you can see in this diagram, it's just showing kind of like two parallel PKIs, one RSA, one MLDSA. For instance, in the end entities, you could have this basically subject information access in each one of those, and it could cross-link. And as long as you know the publishing point before you create the certificate, that can be done. The neat thing is that you can imagine you could use it for things like if you want to look at a related certificate, you could use it for something like hybrid security if you wanted to. So you could have like an RSA and like this example here, MLDSA, but you could also use it for things like cryptographic agility. So you wanted to see if you support newer algorithms or related certificate, or operational redundancy. Maybe you have the same algorithm, but it's used by a different CA and there's something went down in your system. So you could use it for that. And another interesting one is a dual usage use case. So you could have, so maybe you have MLDSA and maybe it's pointing to like an MLChem and you want to do something where you have an SMIME email and you want to reply it and encrypt it back or something like that. So a bunch of different uses. And it's, again, very simple. So go to the next slide here. And you can say there, you might be saying, well, isn't this type of thing already been done before? Very similar things have been done before. So RFC 5697, that's other certificate extension. So that was an extension. However, it used a cert hash, and which was a required field. So it's not possible to do the cross-linking. And also, it didn't have a fetchable URL, which would be nice so you can get it. It's had issuer and serial number, so yes, you could use that, but having a fetchable URL is a nice thing. And then you might remember recently there's the cert auth binding draft, and that one again that uses a related certificate. It's just basically a hash. It doesn't provide any way to actually retrieve that. And again, because the hash is there and it has, it's not, and it's a required field, you can't do that cross-linking. So this is my last slide, basically. So basically, one thing we could add to this is we could add a hash, an optional hash. If we did that, that would allow stronger binding in one direction. You could still do this cross-linking because the hash isn't optional. Hash is optional. But if we wanted to do that, we could add the option of adding a hash in one of the directions. And the last thing is we did address feedback. So Russ, I know you gave us some feedback. Carl Wallace gave us some feedback. We have updated that. We had meant to present this, I think, a few IETFs ago, and it didn't happen. And so anyway, this is our first official presentation of this. We think it's fairly simple. It's just a new subject info access extension that already exists in 5280, and so we'd like to ask for adoption. So.
Okay, so the addition of the cert hash that you talked about has one other pro and con, and that is at the time the first certificate is issued, the other one must already exist.
Yes.
That's a con, sort of.
Yeah.
But you also know that you're getting something that the CA intended.
Yeah.
And that's a plus.
Yes.
So I'm not sure how you want to deal with that, but I wanted to make sure people recognized that situation.
Yeah, and yeah, so it offers that stronger binding, like you said, in the one direction. But yes, that certificate has to be generated for you to have the hash. So the other certificate could still put, a pointer to the other one. It just wouldn't be able to use the hash. So we haven't added that, but if people, there's, like you said, the pro and con of that. We can add that, or we don't have to add it. So any other comments?
Okay, does anyone object to a call for adoption in the next couple of weeks? Okay, hearing none, we'll do that.
Okay, great. Thank you.
I just a quick question. So there
Yeah.
is no way to merge these with the other related certificate thing that's already kind of happened?
Well, the one is an RFC, and I think the other one is for a different type of, actually, is it an RFC too? The multi-auth binding one?
Yeah, I'm not sure actually.
Yeah, I know we had talked to that group
Great.
a year ago, and I think, anyway, sorry, someone else has something to say.
No, it's with the ISG.
Yeah, okay. Sorry. I was just asking if it's
And
already
they
that
have
far
it
in
for
the
a different use case. Yeah, their use
Yeah.
case is slightly different. Yeah.
All right, we'll be moving on to Corey's presentation.
All right, let me see if I'm okay. Can you hear me?
I can.
Okay, great. Awesome. Russ, will you be giving me control, or should I?
I already did.
Awesome. Okay. All right. Ready to go. All right. Yeah, so actually, let me step back to the title page. So myself and Tadahiko and Tomofumi put together a draft. I'll be presenting it here. It's kind of a couple of things at play within the RFC 5280 specification that kind of might have some surprising results. We're looking to potentially close those up. So just a bit of background. I'm going to talk about what indirect CRLs are, because I think a lot of folks in the group already know what these are, but I think it might be some newer material. So what an indirect CRL is certification authorities, like CAs, can delegate the signing of CRLs to other entities. You can basically think of this as like an OCSP delegated responder, but for CRLs. These entities are the CRL issuers are issued an entity certificate with the CRL signed key usage bit asserted in the extension. And you can basically, the definition of an indirect CRL is that they cover certificates that are not signed by the actual CRL issuer. So you have a certification authority, it issues the certificates. It doesn't want to be bothered issuing CRLs for whatever reason. So it issues a CRL issuer certificate to some other entity. It asserts the CRL signed key usage bit in it, and that CRL issuer entity actually issues CRLs on behalf of the CA. And then relying parties consume those CRLs, and they can check revocation status for issued certificates. Support for processing of indirect CRLs isn't mandatory, according to 5280, but several libraries do support it. All right, so to dive into the text within 5280, so section 4123 says that conforming CAs must include this extension, that's talking about the key usage extension, and certificates that contain public keys that are used to validate digital certificates on other public keys or CRLs. So this language makes it pretty clear that if you're issuing a certificate, if the CA is issuing a certificate that's going to be used by a CRL issuer, it needs to contain a key usage extension with the CRL sign bit asserted. However, notably, there is no requirement for non-CRL issuer entity certificates to contain the key usage extension. So if you have for example, an SMIME certificate, there's an entity SMIME certificate, there's no requirement in 5280 that you actually include the key usage extension. So we'll skip then to the processing. So this is the client side, it's consuming, it's doing a revocation check. This section here, 633, is describing the steps that the client takes to validate a CRL to check the revocation status of a certificate. And it says, excuse me, obtain and validate the certification path for the issue of the complete CRL. The trust anchor for the certification path must be the same as the trust anchor used to validate the target certificate. Notably, if a key usage extension is present in the CRL's issuer certificate, verify that the CRL sign bit is set. So what we've seen in a couple implementations is that they actually mirror this language exactly, and that if the key usage extension is absent, there is no check. Basically, that CRL issuer certificate will not be rejected. It'll actually be accepted. And I think that kind of maps to what is being said here, but that might be surprising to a couple folks. What that does is it opens up a scenario where the CA issues a CRL issuer certificate to subject X with key A, explicitly stating the CRL sign key usage bit in the CRL issuer certificate. The CA issues some certificates. It goes and puts CRL distribution points pointing to subject X. It knows subject X publishes CRLs at example.com/foo.dir. And it'll go ahead and put CRL distribution point pointing to that URL. The CA then goes and issues another certificate to subject X with CRL issuer, but with key B, and the certificate that it issues does not have any key usage extension at all. Say, for example, this is a document signing certificate it's issuing to the CRL issuer, so it can sign the the invoices, it's sent into the CA to run CRL issuance services. Somehow someone gets that key B, they go and they use it to sign CRLs, and they go and they publish the CRL at the distribution point that was already specified. Relying parties will then go and download this CRL successfully, as the validation algorithm does not explicitly check for the presence of the key usage extension. And we were able to reproduce this problem with several widely available implementations and libraries. We think this is a pretty, I think, rather surprising behavior. It's just the result of the intersection of the way how the language is written in a couple places. We think that maybe a slight tweak to the language would remediate. That's basically striking that step F that we cited previously. Take that last sentence out and replace it with language that requires both an existence check for the key usage extension, but then also requiring that the CRL signed bit also be asserted in addition to the actual presence of the extension itself. And that would close off that issue. So a couple next steps that we've had. So we did reach out to a couple libraries where we did empirically reproduce this problem. They've been notified, and we've been told that there are fixes in flight, or that they've already been released. I think a couple of the authors also indicated that they would like to see this more formally specified, just so this isn't off-spec behavior. So we would like to formalize the modification, the slight modification of the validation algorithm. So we do have the draft out there. We have it linked. I think circulated on the list about a month or two ago. I think there was one call for support, but we appreciate everyone's input and see if this would be a valuable work item for the group. And I think that's pretty much it on the content, unless there's any questions or comments.
Okay. Does anyone object to a call for adoption? Then that's the next step. Okay. Thank you.
All right. Thank you.
Okay, so I have the pluses and minuses. This was a presentation mainly prepared for IETF 121 in Dublin. And in the meantime, we have quite some progress on the topic. I feel like... Oh, okay. The last sentence was hidden by the control bar. Finally, this is about registering 4 new key purpose OIDs used in basically the rail automation arena, but also reported to us interested to other automation industries. So we would like to get them registered to have interoperability of different vendors' implementations. Currently, the status of the document is that we got working group adoption, and finally we got the working group last call done, and we are heading for request for publication, and Russ is currently doing the Shepherd write-up. To summarize on the purposes the OID shall be used for, this is mainly the quotes from the draft. It's on a general purpose configuration file signing. It's on specific configuration files used to ship new trust anchors. It is on firmware update package signing, and one specific key usage to authenticate entities authorized for safety communication. Any questions on the matter?
Okay, so does anyone object to early allocation here? Okay, then we'll take the next steps on that.
Okay, great. Thank you.
Okay, on to the next presentation. I don't know if David's here. Oh, there he is. Good.
I'm here. How does controlling the... great. All right, so I have one goal in this presentation, which is that at the end of this, you are not sure whether this is a serious proposal or a joke. So have fun. All right, so I'm sure everyone who has done JWP things is familiar with this lovely alg none thing. Instead of including the auth bits, you can just go, nah, I'm just not going to bother. And this has worked great. There's this lovely website that counts how many days since we've had an issue. And let's see. So wouldn't it be fun to bring this to X509? So, okay, this is obviously a joke, right? The rest of this presentation is to convince you that maybe it isn't. To understand this, we need to talk about square pegs and round holes. So if you consider the graph of entities in the PKI, certificates are not nodes, but they're edges. A certificate is information about a subject and information from the issuer that lets you believe that. So it is an edge from the issuer to the subject, and there may be multiple edges leading into a single node. And so if we look at a certificate path, we can we think of this as a list of certificates, but one of the entries in this list is not like the others. The trust anchor, which is usually in the context of something like TLS, not sent by the server, but stuck on by the relying party, is a node, not an edge. You don't need someone to sign it because the relying party already pre-configured it and knows all about it. More generally, there are uses today where you use X509 subject information that you know a priori without needing an edge into it. You've got trust anchors or root CAs. Sometimes protocols will authenticate a TLS server by like something like hashed fingerprint of information. I believe WebRTC does this a lot. But despite this, and then there's also things like when you click through a cert error, people are talking about local devices, all kinds of things people might be doing. But things where people do that today, but systems people build on top of mostly take certificates, which are edges, not nodes. And so the widespread solution here is we stick a self-signed certificate in there. Now, self-signed certs are weird. That signature in there does not really do anything meaningful. If you already believe the subject information, then you didn't need it signed. And if you didn't already believe it, then the signature doesn't help you believe it because it came from a key that you didn't believe in the first place. So really, this is mostly an encoding hack to make nodes look like edges. The self-signature has no security value. In fact, most applications don't even validate it. It wastes bytes with large post-quantum signatures. We now have to worry about well, if this was an end entity certificate, was its key usage allowed to sign X509 certs? We worry about key usage to worry about cross-protocol attacks, but that end entity certificate is a TLS key, and now we have to think about whether the TLS signing payload and the X509 signing payload overlap, and this is just a silly question that we shouldn't have to answer in the first place. If we have a chem key, you can't even generate a signature at all, so it's unclear what you're going to stick in there. So if this field was already being ignored anyway, maybe we can use a less wasteful placeholder. We can define a new signature algorithm or borrow it from, oh yeah, that's a typo on the slides. Russ pointed out that there's already another RFC that defines an OID with the right name, so we can just borrow that OID, possibly, and just use a zero-length signature. Critically, we need to define that this signature is always invalid. Your signature verification function must return false on this thing so that we don't trip up the JWT bug because that was a mistake. But because of this, it means actually everyone already implements this, because your certificate checking function is already obligated to handle unknown signature algorithms and return an error. And this is an unknown signature algorithm. So you implement this by doing nothing. If you already ignore a signature, just keep on ignoring it. You will ignore the placeholder one as well. And if you check the signature, you clearly needed something out of the signature, in which case you should not accept the silly placeholder because it's not actually a signature. So why is this different from the JWT thing? In the JWT system formulation, you are accepting these things instead of actual authentication. So effectively, your verification function is if blah, blah, blah enabled, return true. But this one, you are still rejecting them. We are leaving it alone and keeping it return false. So this is only used when you already didn't care about the signature because for some reason we didn't have like a structure to encode the thing we actually want. And for better or worse, we decided to use self-signed certs everywhere. And so this is the somewhat tongue-in-cheek text I put in the draft right now, which is that you should satisfy these requirements by ignoring this document because you already satisfy them and we don't need to do anything. This is really just a document that says like, if you needed to put a signature in here, but the signature wasn't valuable on the producing side, here's like a canonical OID you could stick in there. Is that not working? There we go. So is this even worth doing? Maybe we should just stop putting square pegs in round holes. I mean, we could. There's an RFC that defines a trust anchor format. I'm pretty sure no one uses it, and I suspect that they're not going to redo everything. There's this TLS raw public keys thing. I've been told from someone who works in WebRTC that like that doesn't work for them for some reason. So if you need other subject information, I guess you need another structure. Everyone uses self-signed certs. Maybe we should do something better for them. Should we use this existing no signature OID or a different one? The OID already exists, which is nice, but the RFC defines them in a different context, sticks a redundant hash in there for an empty string. As far as I can tell, that hash in there also doesn't do anything useful. But since the point was to have a more efficient thing that can be ignored, we may as well not waste 32 bytes by sticking a hash in there that doesn't do anything. It's not an actual conflict to make this OID and certificates do something different because you're ignoring it anyway, but it's a little weird. Someone was talking about doing it with CSRs with ignored signatures, which is yet another one of these square pegs and round holes things. I don't have any strong opinions on CSRs, so I will leave that to other folks. I also don't have any strong opinions on this one. The thing where this OID was previously defined was indeed CSRs, so we need to, like, if we decide we want to do that, then we need to do something about the run-in hash. Yeah, so next steps. Is this a joke or a serious proposal? I don't know. It seemed like fun.
So, David, I don't know what a chem trust anchor is.
Oh, this would be for, so this is like not everything that uses nodes is like a trust anchors. It's not as a trust anchor. Like this is if you're doing, like for instance, if people wanted to do the thing WebRTC currently does with like cert with an entity key that you know ahead of time, and then for some reason you wanted to transmit that in like a certificate, then like then you end up doing that. I know for years ago I had to review code for someone that like they needed to stuff us, they needed to like pass a key in there. For some reason they had defined the system to format the key in a certificate, and they needed to like stick a signature. And so I was like, I guess you could put the empty string if this doesn't make sense.
Sounds
really,
like
that system should not have taken the key as a certificate, but
right. Sounds like they
this whole
should have just
document
passed
is
the
like,
subject public key info and they'd have been
do
fine.
you want to, yeah, this whole document is like, for whatever reason, we have been putting square pegs in round holes for like the entire history of X509. We could either stop doing that and redo all those systems, or we could give them a slightly like more sanded off square peg. And, you know.
Well, as the author of the trust anchor format, I like that one, but the point is, you're right. The signature doesn't matter.
Yeah, for better or worse, nothing ends up using it. And I suspect like a CA will not go, oh, I will just not bother making a self-signed certificate because everyone in the world seems to want one. So
correct. Okay, so I have no objection with moving this forward as long as people understand that all security really comes from the distribution path, right?
Yeah. I think this is like making it more explicit that like this signature did nothing useful in the first place. Yeah.
Yeah, hi. So we're also updating the document. We're going to obsolete RFC 5272 that defined this no signature algorithm. So like, I kind of feel like the baby's maybe, or sorry, the patient is on the table. And so if we want to like drop the useless hash because it is actually useless, it's just there. It's not used for anything. Like there was no text about needing to validate it or anything. You could, you could have it be an option, one of two things, like stick some gobbledygook in here and ignore it, or just send nothing. So I think that that's maybe a possibility as well. So.
Go ahead, Alicia.
Okay, so the situation is basically that if we are talking about things that actually consume the certificates and like need to have the trust anchored, we are talking mostly about like browsers and stuff like that. And they do have those root CAs distributed with them. So like those are not certificates that are sent on the wire, those are stored on the file. And browsers like Firefox already have trust stores that don't require the root in the chain to be an actual X509 file. You can just specify, yeah, this is the public key, and I'm going to trust every certificate that is signed with that key. So there's like no real benefit to have it specified that, yeah, like we have X509 file that has no signature in it. Like if we want to do something like that, yeah, let's do normal OIDs, but then put an invalid signature that's short, and then yeah, you are not expected to verify that signature. So so that invalid signature is fine, and then that file is shorter. But for most cases, like this is basically just a situation where a end user would try to install a new root CA in the system. And for those kind of situation, I think a little bit more self-checks and like sanity checks is better, not worse.
So I don't think it is true that only browsers have like root certificates. I mean, everything that verifies certificates has them.
Sure. But like
the whole point of this is that like the whole point of a trust anchor in general is that this is like pre-configured in the relying party, and you could pick another format for it. Russ just mentioned there's the like 5914 format. You could also just come up with your own because like you only need a few fields. Evidently, that is not what people do across like the entire broader than just browsers space of like systems that do X509. I believe OpenSSL does not have a way to specify them in other things, for instance, and quite a few things use OpenSSL. Like the answer could be, well, maybe OpenSSL should go implement 5914. Like I said, I did this because like I have observed that people like evidently we use self-signed certificates a lot for exactly this purpose. We being like the like ecosystem at large. We could either tell the entire ecosystem like you all need to do it differently, or we can like go and like meet them where they are. And like I have no strong feelings on which one we do. I think if the choice is between putting in a signature that is like invalid, but like we put the right field, or like having an OID that explicitly says like I did not intend for this to be a valid signature. Like, I think having a separate OID is like, then like, at least when you go to look at it, you aren't like confused that something horrible has gone wrong. I mean, for the like that random thing that I had to review years ago when they weren't doing a trust anchor, they were just like their system had a bad format. I think they ended up just putting an invalid signature in there, but it just sort of seemed like not what you were supposed to do. So.
Yeah, I still think that an OID itself is more likely, like if you are writing generic code, then it's more likely that you'll have like an if, also like if no signature, then yeah, I'm not gonna check the signature, instead of having the special case of, am I looking at a root CA? if I am, then I'm not checking the signature. I think it's better to depend on that second, not the former situation.
I mean, I think
Seems
it's like,
more,
like you just sort of like implement this by not doing anything. So, but yes, if someone were to like go special case this, just like if someone were to special case the empty string in the signature field, they would have a bad time. Maybe don't do either of those. Don't implement me, please. Yes.
Hi, yeah, I'm a WebRTC guy. I wrote a draft on how to use raw keys in WebRTC's DTLS handshake. It was a pain. Obviously, it won't interoperate with any existing things. Then I saw David's draft. I implemented it. It all just worked. And it actually interoperates with Chrome's WebRTC stack successfully because they correctly ignore the signature. So for WebRTC, because we use so the certificates are validated by fingerprints that are exchanged in the signaling, and then we use media path DTLS to exchange the media keys. So the signatures are completely irrelevant and made up on the fly every time. The keys are made up on the fly every time. So this is, for the current situation, it's not a big deal because, everybody uses, I think, EC, some elliptic curve signature is tiny. But when we have to go to post-quantum, having an entire post-quantum signature floating around on these things when we're in DTLS and, MTUs count is going to be a big waste, so we'd rather not do it. So I'm certainly in favor of being able to do this, but I guess I don't actually need your approval because I can do it and it just works.
Okay, so at least one person wants this adopted. Does anyone object to a call for adoption where we discuss this more thoroughly? All right, we'll see that next couple weeks. Thanks, David. I think Lynn's going to present. Oh, Sun's going to.
Can you hear me? Yeah.
Yes.
Yeah. Okay. Hello, everyone.
Can I give you control?
Yes, sure.
Okay, go ahead.
Oh, thank you. Okay. Okay. Hello, everyone. I'm Shujo, and I'm very new to this working group and still trying to learn and hopefully can contribute some good ideas. Okay, let me do a quick introduction of our drafts. Okay, next page.
Well, I gave you control. You can hit the pluses. You want me to do it?
Yes, I clicked E.
Okay, there you go. It worked.
Yes. Okay. And I think this idea was maybe initially proposed maybe 6 years ago, and there has already been some discussions, and we still want to have the draft because we find it is very useful for some of our scenarios in our company, and the core idea for this draft is to sign the hash of the second public key, and during the transmission, you can either transmit the hash of the public key or you can transmit the actual value of the public key. And the client, when we receive the the certificate, it covers the public key value to its hash, and then it verifies it. And in the draft, we actually propose some new CSR attributes and some extensions to implement the idea. And there were some existing solutions related to this draft. And we have listed it here, like the one by sorry, I can't speak his name. it cannot support transmit public key hash. And also there was a ITUT standard, and it only allows to use one public key or one signature and account. And also there was a draft by Mike. The idea is to use the external public keys, so you can only transmit the hash of the public key. Okay, can we go to the next page? Okay, thank you. And I want to recall that in the previous draft, in the Thompson notice, it mentioned that the major downside of this proposal is that it requires the large public key, even if the clients don't use it. And additionally, it also mentioned that the dependent protocol needs to be updated so they know how to handle the multiple public keys and multiple signatures. And we try to figure out how to solve these problems in our draft. Mainly for the first issue, we use the pointer plus hash mechanism to avoid sending the large public keys. And for the second issue, we think that it is the protocol's duty to maybe add some extensions so that they can negotiate the actual form of the certificate to handle the multiple public keys. Okay, maybe next page. Okay, as I already mentioned, that the ITUT standard it only allows to use one public key or one signature at a time. Although it actually provides two public keys. Okay, next page. Okay, thank you. And in the and this one, I think is very clear. It only allows to store the public key in a remote location, so the clients need to download it before connecting to some server. Oh yes, next page. Thank you. Okay, so here comes to our draft, and we want the subscriber to maybe generate CSR, so they to use the composite signature idea, so the CSR syntax does not need to be changed. But this can be, but this is not a video. And the CA verifies the CSR and generate the certificate. And as in here, the first public key is in the SPKI field, and the hash of the public key, the second public key is in the new proposed extension. And we also have a flag field, so that you know the extension, the actual value is in the extension, is hash or is the public key. Okay, maybe next page. Okay, and for the certificate transmission and verification, actually the subscriber has the ability to construct two forms of the proposed hybrid certificate. We mean the by value form and the by reference form. For the by value form, we put the second public key directly in the extension, and then we put a true flag in here. And for the by reference form, we put the put the hash value of the second public key and mark the flag value as false. Yeah, and during maybe in the TLS protocol, the subscriber and the relying party negotiate the exact form to be transmitted, And if the rely party suppose post content cryptography, the subscriber will send the by value certificate. And if it doesn't support post content cryptography, can send by reference certificate. So that the relying party will attempt one or two keys from the certificate. If you attempt the by value form, you should cover it to by reference form, and then you can verify the certificate as your. Yeah. The advantage here is that if the relying party don't support post content cryptography, then no post content cryptography keys or signatures will be sent. Only their hashes. And you can still use the traditional algorithms, so keeping backward compatibilities. And the disadvantage is that maybe it's not easy to accept that one can change the content of a certificate. Yeah. Okay, maybe next page. Thank you. Okay, so I think that's all for my presentation, because we just propose some CSS attributes and extensions and give the exact scheme flow of the procedures. Yeah, and I think maybe can you give some inputs for this draft?
There has been significant discussion while you were talking in the chat. I suggest you take a look at it.
Okay.
Mike, do you want to say any of that at the mic?
Have I made my microphone work?
Yes.
Right. So I think this. So yeah. So thank you to the authors of this. I think this is excellent work to explore the things that were bad about draft. That's Truskowski. Exploring the things that were bad and trying to fix them. I think this is interesting work. And so you're right. The tombstone notice says that one of the problems is that you have to send both keys. And I think you have attempted to solve that with, if I remember correctly, it's a layer of indirection with an external reference. By the way, we also have a separate internet draft with lamps that does, we call it external public keys. So that idea, there's a second draft, and I think I've already invited your team to join us on the external public keys draft if you want.
Yeah.
The other problem, sorry. Yeah, we welcome you to join us as authors on external public keys. The other problem with draft Truskowski is that these certificates are very hard to use. When you try to actually use them, if you take a Truskowski certificate, alt public key extension, and you try to sign a PDF, or you try to sign a Windows binary, or you try to sign a TLS handshake, it becomes extremely unclear whether you're supposed to sign with the primary key or you're supposed to sign with the secondary, the alt key. And now you need the protocol to build in some negotiation mechanism. If you're trying to sign CMS, do you do multiple signer infos and that both point to the same certificate? I think the whole point here is backwards compatibility. The whole point here is that you just do this and old clients will ignore it. But when you try to actually use it in a protocol, you lose that property very quickly for most protocols. And now you have to change the protocol, which is defeating the purpose of backwards compatibility. So yeah, I think it died largely because it's hard to use, and I'm not fully convinced that your draft has made it easier to use on a PDF or on a Windows binary.
Oh, okay. Thanks for your question. And I want to mention that.
Okay, so I think the next step is for you to take on that feedback and see whether you want to update your internet draft or abandon it. Up to you. Okay.
Okay, I will try to do that.
Okay. So let's see if Julian's audio works now. Jumping back.
Yeah, I'm here.
Okay, go ahead. I think I gave you control for the slides.
Okay, thank you. Yeah, so as I just mentioned, actually, the main motivation, maybe not writing very clear in the drafting yet. So I would like to say a little bit more. Yeah, the main purpose is that we would like to address the legacy devices. In that case, the legacy maybe cannot update its trust anchor. Yeah, in that case, yeah, how actually different generation of devices. Yeah, some of issued by old root CA certificates. Some actually issued by the new root CA certificate, such that they can still verify each other's certificate chain. Yeah, so this is not just acquire the public key of the new root CA certificate. They need to become a root CA certificate. Yeah, as the trust anchor for old device. Yeah, so I think this is the one thing. Yeah, a number of experts mentioned this one. Yeah, what is the difference from our for our draft and the RFC 4210? Yeah. Okay, next please. Oh, okay, I control it. Sorry. Yeah. So there's the basic idea. So we mentioned this one. Yeah, about basically two rules. Yeah, two approaches to address how to update the root CA certificate. Yeah, so this mentioned already, so I don't explain it now. Yeah, this one illustrates what is the core idea about our proposal. Yeah, basically that means, yeah, we just use the new with old link certificate. Yeah, such that, yeah, the new public key, yeah, for the same root CA can be introduced to the old public key. Yeah, but of course here, yeah, both the old public key and the new public key, yeah, belong to the actually the same root CA. Yeah, legally, yeah, but they're just two generations of the public key. So in this way, yeah, by the new with old link certificate, the new public key of the root CA can be treated like a subordinate public key of the old root CA certificate public key. Yeah, for this version, the number one version now, so we mainly add the new session about testing results. Yeah, so I will talk about the detail about this test results. So basically, we use several, actually 4, open source software package to generate different types of the root CA certificates together with the subordinate CA and also entity CA certificates, and doing cross verifying test. Yeah, and the result shows that actually for different combinations, yeah, so the result is actually positive, yeah, as we expected. So in this test, so we have 3 generations of the root CA certificate. Yeah, each generation is for 10 years simulated. Generation 1 called G1 from 2016 to 2025, exactly 10 years. G2 is similar, but from 2018 to 2017, and G3 from 2020 to 2029. And the signature algorithms are also a little bit different. For G1, G2, use RSA, and G3, generation 3, use ECDSA. So we generate the certificate chain actually, yeah, in each software, and then verify different generations. So get a lot of combination. So result list here. So of course there is a number of time points. So we select, I remember should be 8 of years as a representative case to show the results. The table can be actually looked up in this way. Like here. For 2020. Under the column. Under the column G2 client means if in the year of 2020, if the client is G2, the client certificate chain issued by the second generation CA. And for the row, the second to the last row, it means G1 server. So G1, so in that case, the corresponding cell means the G1 server is connecting with the G2 client. So what the result will be? So it will have two results. What's the answer from the client? What's the answer from the server? So from here, the both cells give OK. OK means OK. Each other can verify the certificate chain from the other side. All this result actually is the right one. Which are our which actually are the answers we expected. For the -1 means it is actually invalid. Maybe at that time, one kind of the certificate chain is not issued yet. For now, it means this kind of the certificate should not be should not be accepted by one of the peer. Okay. So here just some more tables. A little bit numbers. A little bit of several tables. Okay, so as I just mentioned in the first part, so we will do more, to address, more clearly, read more documents about what is the difference about our proposal and the existing certificate management protocols in different documents. I think this will take some time. I hope I can address them better for next meeting in Bangkok. Thanks.
Does anyone have any comments or questions? Okay, I didn't hear you ask for anything other than review and further comment. Is that right?
Not yet. So I would like to communicate with more experts. It's the next meeting.
Oh, okay.
Well, thank you, Ross.
Okay, thank you.
Thank you.
So it looks like we will have time for an update on composite.
I think that's
I grabbed the wrong slides. There we go. So you're doing this, John. I'll give you control.
I think Mike and I will probably do our usual thing. So we just wanted to talk about a couple updates to composites that happened since 121. One of the things I think we mentioned the last IETF, we are aligning with the MLDSA draft, and they have the hash MLDSA, and that caused us to double the number of OIDs. And then, of course, there was all the discussions about the external mu, and if you use external mu, you don't need this. so I was ready to pull the trigger and actually remove all the 15 combinations of the hash composite MLDSA a couple weeks ago, but then further discussions came up about, well, for reasons why some people may still want the hash composite MLDSA. So let me just open that screen a bit so I can see it better. Yeah, so we just thought we'd put together a pros and cons of why should we remove hash composite MLDSA. So the arguments for removing it obviously removes the 14. Actually, I think we're up to 15 now. So instead of 30, we would have 15. So I mean, that would be wonderful. Client software can hash or not hash based on application needs. As the same verifier, right? So the external mu stuff works good for that. And you retain the strong collision resistance of public key binding. So that'd be arguments for removing it. But arguments for keeping it. So we've heard arguments from people about it retains more crypto agility so the implementer will get to choose which hash function. I mean, that could be good or bad, right? They could choose a bad hash function. And with external mu, obviously you need to use the shake, and maybe your crypto implementation doesn't have that. You also need the hash of the public key TR, and also hash composite MLDSA. It does line with the FIPS 204. I didn't estimate it. We hope for some valid reason. So I think we would like to ask if people's opinions on that. Obviously, we probably won't get to consensus. I mean, in the worst case, if we can't get consensus, we'll probably just keep it there. If no one ever uses it, oh well. But I mean, if we all agree that no, we don't need this hash composite, we'll just remove it. So the next item, yeah, I guess I can speak to this. So Falco had asked us about putting, and he did mention it actually at 121. I didn't quite understand at the time what he meant, but now I do. So he asked us to add, if we could add a prefix at the beginning of the domain separator. And the reason for doing this is, so as you probably all know, with the composite signatures, you can pull out the two signatures, right? So you can pull out the traditional and you can pull out the PQ signature, like the MLDSA component. And then if you ask the question, if you can reconstruct that M prime message, so you can see up here, domain length context, if you can reconstruct that. So if you use that with MLDSA, no, because we use the context. But traditional, yeah, you could reconstruct M prime and then have a traditional verifier actually verify that. So if we want to mitigate that, we could use this 32-byte prefix. So then if that known prefix is could be detected by an update to a traditional verifier. Whether someone would want to actually add that into the traditional verifier like RSA or EC, I mean, that'd be up to them, but at least we'd kind of cover all our bases in the draft. We'd basically write some language about that. So I think it probably does make sense to add that. I don't know if people have comments on that, but we just wanted to mention that. So I haven't added that yet, but I can, unless there's objection to that. And then I'll pass it over to Mike for...
I have a quick question, John.
Yeah, go ahead. Yeah, go ahead.
Is this domain, if you add it, going to be different for each of the composite choices, or one?
Yeah. No, so the prefix would be the same. So Falco suggested 32 bytes. So I think it's composite signature algorithms 2025 actually ends up being 32 bytes. So that would be, so on top of this, if you can see my mouse pointer, it would be M prime equals prefix. And then
we cannot see your mouse pointer, but I get it. That's all I wanted to know. Thank you.
So basically just on top of it, because if say in the future someone comes out with, they want to make Falcon composites. So having a hard fixed prefix is going to allow, you could mitigate this now in your traditional verifier, and you would be able to, for all future, be able to continue to mitigate those issues.
Okay, I just want to remind you we have 5 minutes left in the session.
Okay. Yeah, and I will pass it to Mike now to do the...
Right, so the major thing that's come up with chems, composite chem, I mean, we have a bunch of stuff, but the major one that we've dealt with so far that needs working group input is HPKE. So we currently have the document is here's a new algorithm, and we have a section that says here's how you use it in CMS. Chris Wood wants to add also here's how you use it in HPKE. Great, cool. The thing we're stuck on is HPKE needs a deterministic seed-based keygen. Xwing has this, so Xwing defines a deterministic keygen, but that's not compliant with FIPS 203. So you would not be able to take the Xwing keygen and run it through FIPS. And for me, that's a bit of a showstopper. If someone wants to claim that nobody in HPKE land cares about FIPS, that's cool, but that someone else is going to have to make that claim. So we're not quite sure how to proceed here. I think like the Xwing draft and the composite draft have become two different drafts with two different sets of voids for exactly this reason. And I think we've agreed to proceed that way. And yeah, the pull requests we've had so far sort of blur that back together, and we need to untangle that. And we literally talked to Chris yesterday, and I know Chris was going to go talk to Deirdre and Boss. So this is the sort of big design thing that's holding up this draft from doing another version at the moment. Next, what do I have? Yeah, John?
Yeah, I was going to say, and we do know how a proposal of how it could work, but then that would be like basically 3 types of keychains.
I see Deirdre's question in chat. The problem isn't regen from seed, it's that you're doing shake. You have one 32-bit seed, and then you're expanding it with shake to 96, and then passing some of that into MLChem keygen internal. You are very clearly not allowed to do a KDF. It has to be direct output of an approved random number generator. It's that shake line that makes it a problem. If Xwing said, start with a 96-byte seed and chop it up, that would be perfect. But unfortunately, that's not what the Xwing draft says. It has that shake line in the middle, which is problematic.
So Mike, I have control to move to the next slide because I don't anymore. Yeah.
Cool. So the last slide basically says we got the GitHub issues down to 0 for Dublin, which was excellent. And then a bunch of helpful people have been helpful and have put in more issues. So we're not ready for working group last call yet. We need to truck through all of these.
Yeah, so that's where we are with the composites. Any comments about the issues? I guess we can take them to the mailing list too. Because, like Mike said, we want to get these to working group last call.
Indeed, we do. Okay. I've been told by the authors of the MLChem and MLDSA X509 and CMS drafts that they expect us to be ready for working group last call by the end of the week. I'm hoping that happens. Any other questions or comments before we close with 2 minutes to spare? And Sean confirms in chat he just asked for working group last call on one of them. All right. All right. Thank you. We made it. 1 minute to spare. Happy New Year. Bye-bye.
Happy New Year.
Bye-bye.
Happy New Year.
Thanks. Happy New Year, everyone.